Hooray! We have finally arrived at the place we've been building to all term. This is inferential statistics. The title of this chapter is Hypothesis Testing because this is the foundational procedure that we're going to follow in all of our inferential statistics throughout the rest of the term. Here's the logic of hypothesis testing. Remember that we can't measure every person in a population, so we draw samples and we use them to make inferences or guesses about the population. Hypothesis testing is one of the most commonly used inferential procedures. If I were to give a definition of hypothesis testing, it would be a statistical method that uses sample data to evaluate the validity of a hypothesis about a population parameter. I'll take just a moment and expound on that a little. You recall from our first module, that a population parameter is a number that is computed for all the people in the population taken together. So, for instance, if you were to say the average IQ of all the people in the United States, that would be the population parameter. We almost never know the population parameter. In some situations, we've done enough testing that we can give some hypothesized average value. So SAT scores have a population parameter of 500, and IQ scores have a population parameter mean of 100. But most of the time, we don't know what a population parameter is, and so hypothesis testing is to compute, based on a sample, some statistic that is used to make a guess about a population, what the population parameter would actually be. This is a procedure that combines z-scores, probability, the distribution of sample means, everything that we've done so far in the class, and it actually ends up being surprisingly easy. Here's a simplest case example, using a sample mean to test a hypothesis about a population mean. It will eventually become a little more complicated than that, but we can take a sample mean and make some statement about a population mean. We go through a series of 4 steps in a hypothesis test, and I'm going to give you an example of each step. So, step 1, state the hypothesis about a population. An example might be, American adults gain an average of 7 pounds between Thanksgiving and New Year's Day each year. Step 2 is to predict the expected characteristics of the sample based on the hypothesis. The example here would be to predict that our sample should have a mean weight gain of around 7 pounds. Of course, we know because of measurement error, there's going to be some difference between our sample and our sample average and 7 pounds. So it might not be exactly 7, but it should be something around 7 if our guess is right. Step 3 is to obtain a random sample from the population. We would select a sample of 200 American adults and measure their weight change to see how much weight they gained or lost during that month between Thanksgiving and New Year's. And finally, we would compare the obtained sample data with the prediction that we made from the hypothesis back at the beginning, where we said that we thought they were going to gain an average of 7 pounds. And if what we saw was consistent with our hypothesis, then we say, our hypothesis is reasonable, we're probably right. So, if that's what happens, then if our average weight change is near 7 pounds, then we accept our hypothesis. But if what we see is discrepant, different from what we guessed, then our hypothesis is rejected. So, if in that case our average weight change is far from 7 pounds, then we reject our hypothesis. In any given experiment, we will start with a research question. That often is something like, what effect will a treatment have on individuals in the population? It doesn't always have to be a treatment, but usually we manipulate some things. So it's usually a question surrounding what is the impact of an independent variable on individuals in the population. And that treatment doesn't have to be like therapy. It could be anything we've done. So in the last example, the treatment was the holiday season. So what happens because of the holiday season that changes people's weight? For simplicity, we're going to make two basic assumptions here. The first assumption is that we know the population mean before the treatment. As I said before, that's almost never the case, and so this is an oversimplified example in this chapter, and we're going to see what we can do in future modules when we don't know the population mean. But for simplicity's sake here, we're going to say we know the population mean before the treatment, and if there is an effect, it's just going to add or subtract some constant amount from each score. This will change the mean, but will not change the shape of the distribution or the value of the standard deviation. This is something we learned in an earlier module. If you add or subtract some amount from every score in a distribution of scores, then the mean will change by that same amount. If you add 3 to every score, the mean will also increase by 3. And the standard deviation will not change. This means our treatment has to be an additive or subtractive effect. If it were multiplicative, where it takes small values and results in still small values, but takes big changes or big values and makes even larger changes from them, then we couldn't use these kinds of statistics to evaluate those treatments. So an example here is given in this figure where we know the population before treatment. It has a mean of 80 and a standard deviation of 20. It doesn't matter what these scores are. We could call them memory or speed driving in a car or weight of some object or whatever. It doesn't matter what it is, but we know the population's mean and standard deviation. We give it some kind of treatment, and after the treatment, we don't know what the mean is. We're trying to assess what it is, but we do know that it has the same standard deviation because, like we set up above, the treatment just has an additive or a subtractive effect. So the standard deviation will not change no matter what the treatment did. If the treatment didn't work, it will still be 80. If it did work, it might be higher or lower, but the standard deviation will not change. This population here is hypothetical since we never actually treat the whole population. So to show that in a figure, I will illustrate that from the point of view of the hypothesis test, the entire population receives the treatment, and then a sample is selected from the treated population. So it might be a known original population with a mean of 80, and we give it some treatment, and the treated population has an unknown mean, but we draw a treated sample from that population, and we try to measure the mean of that population from the treated sample. But in real life, we can't do that, and so instead, we take a known original population, draw a sample, give it a treatment, and then we take that treated sample to imagine what the whole population would like if every single person in the population had received that treatment. Going back to the first beginning of the presentation where I illustrated 4 steps of a hypothesis test, I'm going to rephrase these in simplified terms. Step 1 is state the hypotheses. Step 2 is to set the criterion for a decision. Step 3 is to collect the data and compute some sample statistics. And step 4 is to make a decision. We're going to walk through these 4 steps and see them in action in a very concrete example of a research study. Let's suppose that you wanted to know whether mild electrical brain stimulation can help students to learn math. The general population has a known mean of 80 and a standard deviation of 20 on a particular standardized math test. You plan to take a sample of 25 students and stimulate their parietal lobe while they study. Now, just so you know, this is not a far-fetched, silly example. People have done research like this before to demonstrate that mild electrical brain stimulation over the parietal lobe can actually help students to learn math. So, hopefully that's what we discover as we walk through this example. Step 1. State the hypotheses. The null hypothesis states that the treatment had no effect. It could also be that there is no change, no difference, or no relationship, hence the term null, nada, nothing. Null hypothesis means we guess that, or we hypothesize that there is no relationship, there is no change, the treatment had no effect, nothing happened, nada, nothing. We designate in statistical terms an example as using the symbol capital H sub 0 to designate the null hypothesis. And then after that, we write whatever it is. In this case, we're going to say that we think the mean is equal to 80 if the treatment did not work. If there was no effect, zero effect, then we say the mean of the treated folks after they've received the electrical stimulation is still 80, just like it is for everybody else. The alternative hypothesis, or research hypothesis, states that the treatment had an effect. We could also say that there is a change, there is a difference, or there is some relationship between two variables. This is designated in statistical notation as a capital H followed by a sub 1. This stands for the alternative to 0. So the alternative hypothesis, H1, is that the mean of the people who have been treated is not equal to 80. If the electrical brain stimulation did something, their scores should be higher or lower than 80, but it should not be 80 if the brain stimulation actually had an effect, if it actually enacted some change. So these two outcomes are mutually exclusive and exhaustive. One and only one of these two statements must be true. The mean of your population, the reason why we designate this as mu instead of the mean, M, capital italicized M, is because we're hypothesizing something about that imaginary population. We're never going to treat the whole population, but we're making a guess about that whole population. And so we're saying here that the population of people who've received electrical stimulation is either equal to 80 or it's not equal to 80. But one of those has to be true. It either is or it isn't. But both of them can't be true, because it either is 80 or it's not 80, but it can't be both 80 and not 80 at the same time. And so one and only one of them must be true. They are mutually exclusive and exhaustive. Our data, our sample, determines which one we should reject. So one of these is going to be true and the other one is going to be false, and we're going to reject the one that's false. Now we're still talking about step 1, which is to state the hypotheses. On the last slide, the alternative hypothesis stated that there was, quote, a change, but it didn't specify the direction, like if it's going to get better or worse. For some research questions, it's better to state a predicted direction. For example, the alternative hypothesis could be that the treatment will increase test scores, but we're going to touch on this later. The second step of the hypothesis testing process is to set the decision criterion. Obviously, the mean of our sample isn't actually going to be exactly 80 because, as you remember, sampling error. Whenever you draw a sample, it's never going to be exactly the same as the population, and so we're going to have some discrepancy. But how do we know if we can reject the null hypothesis that the mean is 80? We have to create a null distribution. This is all the sample means that we could get if the null hypothesis were true. So imagine that the null hypothesis is true, that the electrical stimulation doesn't actually do anything. And from that population, where the electrical stimulation didn't do anything, we drew sample after sample after sample after sample after sample, and we computed the average of each one of those. It should be centered around 80, but some of the samples are not going to be exactly 80. So this right here is the known population before treatment, and this right here is the sampling distribution, which we drew from the population, sample after sample after sample, and these sample means will mostly be around 80, but some will be a little higher and some will be a little lower, and the standard error of the mean from this sampling distribution is computed, as you know now, using sigma over the square root of n. In this case, 20 is sigma. The sample size was 25. That was on the last slide. And so we put that into the equation, and we can figure out that the standard error of the mean here is 4. So most sample means will be somewhere between 80 and 84, or on the lower side, 80 and 76. Some will be a little further out than that. But most of them, 70% of them, will be between 76 and 84. 95% of them will be between 72 and 88. Then we change the null distribution into z-scores. So we put the mean down here as 80 and the standard error of the mean here as 4. But here, when you change the whole thing into z-scores, this becomes 0 and 1. Then we divide the distribution of sample outcomes into 2 parts. Those that are likely if the null hypothesis is true are those here in the center. In the tails are those that are very unlikely if the null hypothesis is true. So let me just remind us in terms of the research question that we're working on. The null hypothesis is that the electrical stimulation didn't do anything. If it didn't do anything, then the sample means should be somewhere around 80. The mean here is 80. And most of them should be somewhere around here. But if we draw a sample and it happens to be the one over here, or one over here, or one over here, that lands in the tails of the distribution, then we would say those are very unlikely to be drawn by chance if the null hypothesis is true and the electrical stimulation doesn't really do anything. So, the alpha level, or the significance level, is a probability value that we use to define what these blue tails, these very unlikely outcomes, are. The critical regions, those blue shaded tails, consist of the extreme sample means that are very unlikely to be obtained if the null hypothesis were true and the electrical stimulation really didn't work. The boundaries of the critical regions are these lines right here. They are how we define what is normal and what is extreme or unexpected. The boundaries of the critical regions are determined by that probability level that's set by the alpha level. So this alpha level, or significance level, defines these lines right here, where they are. What would the z-score boundaries be with an alpha level of 0.05? If we have an alpha level of 0.05, that means 5% of the scores should be in the tails of the distribution. That is not 5% in each tail. We take this 5% and we split it between the 2 tails here. So that would mean that the middle 95% are here, and the highest 2.5% are up here, and the lowest 2.5% are down here, because 2.5% plus 2.5% equal 5%, our alpha level. If you take a moment and go to your table B.1, you can find the z-scores that are associated with 2.5% in each tail. You should have discovered that the lowest critical region there in the lowest 2.5% was negative 1.96 and positive 1.96. So these boundaries separate the highest and lowest 2.5%. What would the z-score boundaries be with an alpha level of 0.01%? Again, if we're looking for the middle 99%, we're separating the 0.01 into the lowest 0.5% and the highest 0.5%. Because here we're looking at 0.01, we have to divide that in half across the 2 tails and put the middle 99% in the middle. If you go to your unit normal table, B.1, you should be able to figure out what is the z-score associated with 0.5% in a tail. you should have discovered that it was negative 2.58 and positive 2.58. Okay, finally, what would the z-score boundaries be with an alpha level of 0.001? In this case, this is 0.1%. So we have to divide the 99.9% in the middle and take this 0.1% and separate it into the lowest and highest tails at 0.05% in the lowest and 0.05% in the highest. Can you figure out from your unit normal table what the z-scores should be? Hopefully you discovered that it was negative 3.3 and positive 3.3. By going through these multiple examples, you should be able to see that the alpha level, or the significance level that we're setting, is separating the probable values in the middle from the unlikely scores in the extreme ends. But that if we're using what's called a two-tailed test, where we separate the two tails and say that the alpha level is for both of them, then we have to take the alpha level and divide it in half. The critical regions for an alpha of 0.05 are shown here in this graph. Again, those were negative 1.96 and positive 1.96. The extreme critical region were these 5% that were divided in half at 2.5% in this tail and 2.5% in this tail. This 80 is the mean of the population if the treatment doesn't have any effect on math scores, and the people who have an electrical stimulation of the brain still continue to obtain the same math scores as everybody else. Every once in a while, we might, just by chance, get a score that's out here in the tails when we draw a sample of people from that treated population, and every once in a while we might get a score out here in the other upper tail. But not very often, only 5% of the time. 95% of the time, when we draw a sample of people who've had electrical brain stimulation, we should find that if it doesn't work, if the null hypothesis is true, that their mean falls in the middle of this distribution. So in our brain stimulation example, we're going to use this alpha of 0.05. And we're going to reject the null hypothesis if the sample has a z-score that is below negative 1.96. And we're going to reject the null hypothesis also if it has a z-score that's above 1.96. So if it falls in the lower end or the upper end, then we're going to reject the null hypothesis and conclude that it's possible that we just happened to get a very low scoring or very high scoring group of folks when they took the electrical stimulation. But a more likely explanation is that the treatment actually did something. That the reason why the sample mean is so high is not just because we accidentally got a high scoring mean, though that's possible. Rather, it's probably here because the treatment actually did something that made their scores much higher than the 80 that the rest of the population is when they don't receive electrical brain stimulation. Okay, so step 3. Collect the data, and at last, the moment we've been waiting for, we can now take our sample of 25 students and electrically stimulate their brains. But notice that we collected our data after the hypotheses were stated, and we've established our decision criterion. This must always be the case. We have to do that because if we collect our data before we set our hypotheses or before we set our decision criteria, then we could tamper with the decision criteria and kind of tweak things to say, oh, I meant to say an alpha of 0.01, or oh, I meant to say a one-tailed test, or something like that, that skews the results of the hypothesis testing procedure to be in our favor so that we can say, our treatment worked, even though objectively it might not have if we had set the hypotheses before we collected the data. So step 3 continued is to compute our sample statistics. So we collect the data, we compute a sample statistic. We compute the sample statistic in this case, a z-score, but in future modules, it's going to be other kinds of statistics. And we're going to show the exact position of the sample within that distribution of null means, if the null hypothesis is true. So the z is computed, as you know, by the mean of the sample minus the mean of the population divided by the standard error of the mean. Or, I'm going to say this in words, the z is equal to the sample mean minus the hypothesized population mean divided by the standard error between sample means and the population mean. Remember, standard error is the typical distance that a mean on average will be from the population mean. So, the top of the z-score formula is telling us how far apart our sample mean is from the population mean, and we're putting that in terms of how far we expect it to be just by chance. The standard error is how far we typically expect it to be. So if this on the top is much larger than what we expect it to be just by chance, then we will have a large fraction, and the z will fall far outside the standard, far in the tails of the sampling distribution. So the bottom of the formula is measuring the standard distance that ought to exist between a sample mean and the population mean, and we're using that as a benchmark for how big our difference between our sample mean and population mean really are. So recall from our example that the population mean is 80 on this math test, and the standard deviation is 20 on that same math test when they don't have brain stimulation. So in our z-score formula, we can say we draw a sample of 25, and the mean of that sample was 89. Plug in your values, and we figure out what would our z-score be in that case. Remember, 80 is the population mean, 89 is our sample mean, so how far apart our sample mean is from our population mean is 9 points. 89 minus 80, 9 points. How far do we expect it to be on average? Remember, the standard error of the mean we computed on a previous slide was 4. So we're putting this 9-point difference in terms of the 4-point difference we expect there to be typically just by chance, and we say we actually have more than twice that large a difference here, 2.25. So the z-score falls far in the tail. 2.25 is more than 2 standard deviations above the mean of the null hypothesis sampling distribution. Let's say instead that we drew a sample of 25 and the mean was 84. What would be the z-score? Okay, so in this case we'd put 84 here minus 80, and we'd say we have a 4-point difference divided by the 4-point difference we expect there typically to be, and we say, oh, actually, we have exactly the amount of difference here that we expect there to be, and the z-score is 1, so this is only 1 standard deviation away from the sample mean, a totally typical z-score if the treatment didn't have an effect. So if the sample statistic is located in the critical region, then the null hypothesis is rejected. But if the sample statistic is not located in the critical region, the researcher fails to reject the null hypothesis. Remember, the null hypothesis is that statement that we're saying the treatment didn't do anything. It actually didn't have any impact on math scores. These are the critical regions, right here and here. This is not the critical region, and so we have to place our z-scores. Remember, does our z-score, the first one, of 2.25, fall in the critical regions? Look at the critical regions. It's beyond z of 1.96 or negative 1.96, and our z-score is 2.25, which falls past the 1.96. So, should we reject the null hypothesis? Yes, we should reject the null hypothesis because it falls in the critical region. It's possible that we got a z-score of 2.25 just by chance, just because the people that we drew happened by chance to be very good at math. But that's unlikely. Mostly what we can conclude is probably that the electrical stimulation worked and improved people's math scores to put their average score way out here in the tail. The reason why it would fall out here is because this isn't just by chance. The treatment probably actually worked. But remember, we computed two z's. We said, what if we drew a sample of 25 and their average was 84? And we computed from them a z-score of just 1. Does that z-score of 1 fall in the critical region? No, it falls right around here. And so should we reject the null hypothesis? We can't reject the null because it seems like that's the kind of thing we would typically expect to find just by chance because of sampling error. If the treatment didn't have any impact and we were just measuring people's math scores in samples taken randomly, you might expect to find, just because of sampling error, that one of your samples would have a mean of 84, and that's totally fine. So, if we had a z-score of 2.25, then we would reject the null. If we had a z-score of 1, we could fail to reject the null hypothesis. That means we couldn't reject it. Now, this verbiage of rejecting or failing to reject it might seem kind of weird, but I have an analogy here of a jury trial that might help it to make better sense. If you consider a research study in those terms, a trial begins with the null hypothesis of not guilty, because, remember, a defendant is innocent until proven guilty in our justice system. So we start by saying the suspect is not guilty. Then, just as a researcher tries to gather evidence to reject that null hypothesis, police and prosecutors gather evidence to try and prove that the defendant is actually guilty. If they gather a sufficient amount of evidence against the defendant, then the jury rejects the null hypothesis, that is, innocence, and finds the defendant guilty. Remember, the null hypothesis was innocent until proven guilty, and if we prove them guilty, then we can reject that null hypothesis and say they're guilty. But with insufficient evidence against the defendant, the jury fails to convict. This is critical right here. They fail to convict. They do not conclude that the defendant is necessarily innocent. In the same way, researchers with insufficient evidence fail to reject the null hypothesis, realizing that the treatment might actually have worked a little, just not enough to convince themselves or other scientists that it worked. In a jury trial, we might say we didn't provide a preponderance of evidence to suggest that the person is guilty, and so we let them go and we don't convict them, even though we don't know whether they did commit the crime or not. Practically speaking, the person is considered not to be guilty, or, in other words, innocent, but we don't know that for sure. So that's the reason why we can't accept the alternative hypothesis necessarily without rejecting the null. That's what we're actually doing here, is we're rejecting the null hypothesis, that is, the treatment didn't work, and therefore, because we've rejected the null, we can say the treatment did work. But if we don't reject the null, we can't accept the null and say the treatment didn't work at all. We just have to fail to reject it because it might have actually done some good. We just don't know until we find better evidence. There is some degree of uncertainty in hypothesis testing. Remember that this process is inferential. It uses limited information just from a sample to make a statistical decision, and then we draw a general conclusion. But errors are possible in this process. Usually, the samples we draw have means that are pretty close to the population mean. Remember, from previous modules, we learned that about 70% are within one standard error, and about 95% are within two standard errors. So, the middle 70% here are where we would expect some samples to appear just by chance, and within two standard errors, we would expect 95% of the samples to appear just by chance. But sometimes a sample mean might not be close to the population mean. About 5% of the time, they're more than 2 standard errors away. And so if we find one out here in the tail, and we say, we think the treatment actually worked, it made scores lower or it made scores higher, we might be making the wrong decision. These type 1 errors are when a researcher rejects a null hypothesis that is actually true. So in other words, the researcher concludes that a treatment is effective when really it isn't. So if we were in this example to find a z-score of 2.25 like we did after gathering people and electrically stimulating their brain, and it lands in the critical region, and we say, wow, they got an 89 on this standardized math score that's supposed to just have an average of 80, that's way better. 89 is way better than the typical 80 that most people get. And we'll conclude that the treatment worked. But sometimes we might be deluded into thinking that it worked when it really didn't, and we just happened by chance, by bad luck, to grab a sample of people who were really good at math. And we think that the reason why our sample scored so highly is because the treatment, the electrical stimulation, made them perform highly. But really, we just got bad luck. We just found a group of people who were good at math. So if that happens, that's called a type 1 error. Another example might be that some clinicians want to know whether you can treat overeating with an app that sends an inspirational message every day. Do your body right, or love yourself. It doesn't really work, but we just happen to accidentally draw a sample of skinny people, so the mean fell in the critical region. And then we think, oh look, this group of people weighs less than everybody else, so this app must have worked. That's a type 1 error. It's important here that we understand alpha level is actually the probability that a test will lead to a type 1 error. That's the chance that a test will be wrong. So if you have an alpha of 0.05, we can expect to make a type 1 error about 5% of the time. That means that 5%, or 1 in every 20 published studies, could be a type 1 error. That's the kind of error where just by chance we got a group of skinny people or people good at math, and we thought that the treatment worked, but it really didn't work, and we wrote our paper and concluded that it worked, but we were actually wrong. And only God knows that, but we scientists think we made the right decision, and really we made the wrong one. The only way you can correct for type 1 error is to replicate research, to do it multiple times in multiple different labs to see if you keep getting the same results over and over again. If you do, then you can trust that probably each one of these studies is coming to the same conclusion because the treatment actually worked. But if once the treatment worked and you try to repeat it and it doesn't work again and again, then you say that was probably a type 1 error where we thought it worked, but it really didn't. Type 2 errors are the opposite. It's when a researcher fails to reject a null hypothesis that is actually false. So, in other words, the researcher failed to say a treatment was effective when really it was. An example of this is some clinicians want to know whether you can treat depression with a drug to boost serotonin. It actually works, but it only improves their depression scores a little bit, so their mean still falls within that middle 95% of the distribution, and the researchers say, the treatment didn't work. The mean is about what everybody else's depression scores are typically, even without the serotonin. The probability of making a type 2 error is not easily identified. We can't determine it unless we have multiple variables and lots of information. This table illustrates what type 1 and type 2 errors are, given a researcher's decision and the actual situation, the truth of the matter, what's really going on. Now, only God knows this, the truth of the matter. But the researcher is having to make some inferential decision, some guess about what really is happening, even though they don't know for sure. So, if there is no effect, and the null hypothesis really is true, and the researcher fails to reject the null hypothesis because it really was true, they would be making the correct decision. If an effect exists really in the real world, that is, the null hypothesis is false, and really something is working, the treatment works, or there is some relationship, and the researcher rejects the null hypothesis, then that's also a correct decision. That's what you hope happens. But sometimes, if there is no effect, and the researcher rejects the null hypothesis and says, there is an effect, that's a type 1 error. And if there really is an effect, but the researcher doesn't detect it because it's too small, and so they fail to reject the null hypothesis, and they say, the treatment didn't work, that's a type 2 error. This is indicated by the probability called alpha. This is indicated by beta. This alpha is the same alpha as before when we said the 0.05. That's to say the type 1 error will be 5% if we use an alpha of 0.05. It'll be 1% if we use an alpha of 0.01. Whatever our alpha is, that's how often we're going to make a type 1 error. So earlier we calculated those boundaries of critical regions associated with various alphas. We said if we have an alpha of 0.05, then here's the critical regions. And if we have an alpha of 0.01, then here's the critical regions. And if we have an alpha of 0.001, then these are the z-scores that bind the critical regions. These alpha levels also determine the probability of making a type 1 error. So you might be tempted then to just choose the largest alpha level so we don't get a type 1 error, right? Because you might say, like, I don't want to be wrong, so I'm just going to choose this alpha of 0.001, and then it'll have to be way far out in order for me to say the treatment really worked. Then I'll never be wrong. The problem with that is the smaller your alpha, the more likely you are to make a type 2 error. That is, to say the treatment didn't have an effect when it actually did. So if you select this alpha of 0.001, and these are your boundaries right here and here, and you collect a sample and you treat them with some treatment like an electrical brain stimulation, and their score falls out here, way in the tail, way far out in the tail, but not beyond that point right there, then you have to say the treatment didn't work, even though it did. So if you select a more stringent alpha in order to avoid making a type 1 error, then you'll make a type 2 error instead. Thus, type 1 and type 2 errors are inverse of each other in some respects. I'd like to talk for a moment about how these hypothesis tests are discussed in the literature. A result is statistically significant if it is very unlikely to occur when the null hypothesis is true. Sometimes we just use the word significant instead of statistically significant. But if we reject the null hypothesis, that is because it's very unlikely that we just got this extreme value by chance. In APA format, you always report that you found a significant effect, report the value of your test statistic, and report the p-value of your test statistic. So I've got here a couple of examples of how that looks in APA format, depending on which of the z-scores we're talking about. Remember, we computed two. One was 2.25 and one was 1. So if we reject the null, it sounds like this. Electrical stimulation of the scalp near the parietal lobe had a significant effect on the mathematics test scores for the students, comma, z equals 2.25, comma, p less than 0.05, period. If you fail to reject the null, it sounds like this. The sample did not provide sufficient evidence to conclude that the brain stimulation had an effect on mathematics test scores, comma, z equals 1, comma, p greater than 0.05. What you should note from these two write-ups is that we separate the sentence from the test statistics by a comma, the test statistic letters are italicized, and the test statistic itself always comes before the p-value. This p-value is either less than or greater than your alpha, whatever you set your alpha at. So if you chose your alpha at 0.05, like we did in this example, then that's what you put here. If you set it at 0.01, then you put that, or 0.001, whatever your alpha is. APA format used to require you to write your p-values like this, in the example I've shown, greater than or less than the alpha. Now it requires you to list the exact p-value, but I'm not going to require you to do that in this class. Usually a computer will give you that value, and you'll just list p equals whatever the value is. The other thing I want you to note in this example is that in the second case where we failed to reject the null, we did not say the brain stimulation didn't work. We said the sample did not provide sufficient evidence to conclude that it worked. So again, we're failing to reject the null. We're not accepting that there was no effect. The critical regions for a standard test. Some students get confused about p less than or p greater than 0.05. Remember, you reject the null when you find an extreme low probability value that's located in the tail of the distribution. Thus, the probability of finding a value in the tails is less than 5%. So here it's 2.5%, here it's another 2.5%. And how often will you be able to find a a sample mean in these tails? It will be less than 5% of the time. That's the reason why we say less than 5%, p less than 0.05, if we reject the null hypothesis. But if we fail to reject the null hypothesis, then the p is greater than 0.05 because this is the large portion. This is 95% of the scores fall here. How often will you get a sample mean that falls in this range? 95% of the time, so it's much greater than your alpha. This is the greater portion of the distribution. You're very likely to get the scores here. These are the smaller parts, so it's less than. You're very unlikely to get scores here. We do make some assumptions when we perform a hypothesis test with z-scores. Mathematically, we have to start with these assumptions, otherwise the statistics break down. In practice, researchers don't concern themselves too much with these assumptions because you can't assess some of them, and the tests seem to work fine even if you don't meet them all. But you should still understand what's being assumed, because if you violate these assumptions too dramatically, then your statistic can't really be trusted. So, the kinds of things we assume before running a test are that we random sampled. Remember, that means that we make sure each person in your population has an equal chance of being selected. That we didn't just pick whoever we wanted to, that we gave everybody an equal shot of being drawn from the population. These are independent observations. Again, we learned about that before, that the moniker independent before random sampling means that you replace the person before you draw them again, and it also means that the people that you drew weren't related to each other. Now, I've given an example here, like you don't select several kids from the same family as participants, but it's not just family relations I'm talking about here. It's also that they're not connected in some fashion, because that will bias your statistic. If they are, like, if you select people who are just very good friends with each other, or only people who are psychology majors, but you're trying to represent the entire Central Washington University campus, then these kinds of things would not be independent of each other. They would be related in some fashion. The value of your sigma, or standard deviation, has not changed because of the treatment. We talked about that at the beginning of the presentation, because we have to use the sample standard deviation to estimate the unknown standard deviation of the population. If the treatment changes the standard deviation, then we can't estimate the population's unknown standard deviation. And so we have to just trust that these are additive effects rather than multiplicative effects. And finally, a normal distributed sampling distribution has to be extant because the unit normal table assumes a normal distribution. Remember, your sample sizes of 30 plus ensure this. So when you use the unit normal table, that's B.1, you can only get those percentages, those p-values, if it's a normal distribution. And that's okay because, like I said, if we have a sample size of 30 or more, then our sampling distribution will be normal even if your population isn't. But if your population is normally distributed, it's okay to have sample sizes less than 30 because then it will be normal too. Okay, there are some factors that influence the outcome of a hypothesis test. The size of the difference between the sample mean and the original population mean will influence how able you are to reject the null hypothesis. If you have larger discrepancies, then you'll have larger z-scores. Like in this case, the sample mean is very close to the population mean. That small discrepancy means that we will not be able to reject the null hypothesis. But if it's far out in the tail, then we can say that's so far away from the population mean that the treatment probably worked. It wouldn't be that high just by chance, would it? I mean, it could be every once in a while, but so rarely that this is probably not that time. This probably means the treatment worked. Variability of the scores can also make you more or less likely to reject the null hypothesis. If you have more variability, that yields a larger standard error. So remember, we had this figure in an earlier module where if the sample here has scores that are all clustered together and a treated sample has scores that are also clustered together, then this limited variability within each group, because they're all clustered close together, there's not much variability. That means that you're going to have small standard errors. These do not fall very far from the population mean of each group, and that means that you're going to have very low standard errors that make it easy for you to reject the null hypothesis. But if you have a lot of variability, like if the scores in the white group are all spread apart and the scores in the blue group are all spread apart, then you might have the same mean difference, but your standard error, the typical distance that each of these scores fall away, is going to be larger, and so you're going to find that it's more difficult to reject the null hypothesis in this kind of situation. The number of scores in the sample is also going to determine whether you can reject the null or not. A larger n size yields a smaller standard error. So if you have, as we've used this online example many times, if you use an n of 5 for each sample that falls down here and you compute its mean and then create your sampling distribution from that, it's going to be much wider. Each sample will be very far from the population mean. But if you use larger samples like an n of 25, then the standard error is much smaller, and the typical distance of each of these sample means is much lower. It's much closer to the population mean. Okay, we've talked about two-tailed hypothesis tests. Now I want to talk about directional hypothesis tests. The standard hypothesis testing procedure is called two-tailed or non-directional because the critical region involves both tails to determine if the treatment either increases or decreases the target behavior. It could be either one, and we would say it had some impact. However, sometimes the researcher has a specific prediction about the direction of the treatment. And when a specific direction of the treatment effect can be predicted, then it can be incorporated into the hypotheses. In a directional, one-tailed hypothesis test, the researcher specifies either an increase or a decrease because of the treatment. If that were the case, then we put all of our 5% of the alpha in one tail instead of both tails and splitting it across the two. Here's an example. Using our same brain stimulation experiment, let's say that we select a sample of 25 participants, and this time they have a mean of 87 on that math test. Compared to the population that had, remember, a mean of 80 and a standard deviation of 20, we want to know, do our data suggest that the stimulation improved their math scores? So let's go through the 4 steps of a hypothesis test. Step 1 is to state the hypotheses. In this case, instead of saying that the mean is different from the population mean, we would say the test scores are increased rather than different from. And then the null hypothesis would be that the test scores are not increased. In statistical notation, we would write this out like this. The mean is greater than 80 because we're thinking that they increased the mean above the typical people in the population. So the average score is greater than 80. And the null hypothesis is that the mean is less than or equal to 80. Even if the electrical stimulation got much worse, if the electrical stimulation made their math scores much worse, we don't care about that because all we've asked is, does it improve their math scores? Then we set the criteria for a decision. So we're going to say that when we have a sampling distribution here, we've computed the standard error of the mean as 4, just like we did before, and we put all of our critical region, all of our alpha here, in one tail rather than in both tails. So only if the sample mean falls in this region will we reject the null hypothesis. If we have an alpha of 0.05, what percentage would go here? That would be 5%. So, what is the z-score boundary of the critical region? Hopefully you discovered that that should be 1.65. The critical z, therefore, is 1.65. And if we find a z-score of our sample that's greater than that, that means the treatment worked. If it's less than that anywhere in the rest of this distribution, that means we're saying it didn't improve their scores. So step 3 is to collect the data and compute a sample statistic. Here we've computed the z as 87 minus 80 divided by the standard error of 4. We have a distance of 7 points away from the population mean, but typically on average we can expect there to be about 4, so the distinction here is 7 divided by 4, or we have about 1.7 times higher a score than we would expect typically just by chance. This z-score of 1.75 falls beyond the z-score of 1.65, and so we can make a decision here that the stimulation produced a significant increase in the scores. And then, in APA format, we have a comma. Z equals 1.75, comma, p less than 0.05, comma, if it's a one-tailed test, we specify that. If it's a two-tailed test, we don't have to specify because almost all statistical tests are two-tailed. But if you have a one-tailed test, that needs to be specified. So we put here one-tailed test. Now here's the thing about one-tailed tests. They allow us to reject the null hypothesis with relatively small differences, provided or as long as the difference is in the predicted direction. So if we think there's going to be an increase, and there is an increase, it doesn't actually have to be that big of an increase in order for us to say, the treatment worked. A two-tailed test requires relatively larger differences, regardless of the direction of the difference. In this most recent example, if we had used a two-tailed test like this, with a critical region in both sides, then the critical z would have been plus or minus 1.96 instead of 1.65. And we wouldn't have been able to reject the null hypothesis because the z we computed, in the case of 87 minus 80 over 4, was just 1.75. So that would have fallen somewhere over here, and the critical z value right here is 1.96. So we wouldn't have been able to reject the null hypothesis with this sample mean if we hadn't had a one-tailed test. In general, two-tailed tests should be used unless there is a strong justification for a directional prediction. Most peer-reviewed journals in which science is published today will not accept your paper if there is a one-tailed test. Although commonly used, some researchers are concerned about hypothesis testing because the focus of the test is on the data, not the hypothesis. When the null hypothesis is rejected, it's because we're saying this sample is very unlikely if the null is true. But the fact that the sample is unlikely suggests that the null hypothesis is also very unlikely, but that's not what the test has demonstrated. We kind of wish it was, but we haven't said that the null hypothesis is unlikely. All we've been able to say is that the sample we obtained would be unlikely. So there's a little bit of a logical leap there that is difficult for some people to accept. Now, just because we have a statistically significant result does not mean that we have a meaningful result. Significant effects are not always substantial. Consider, for instance, if a diet program reliably helps people lose 1 pound. You write your hypotheses, you set your criterion, you draw your sample, you compute your statistic, and sure enough, the treatment group lost a statistically significant amount, about 1 pound. Psst, nobody cares. Effect size is an ability to measure the absolute magnitude of a treatment effect, regardless of the sample size. Now, the way that this can happen is because if you have a large enough sample size, almost any difference can be statistically significant because the sampling distribution becomes so skinny that even a 1 pound difference can be statistically significant. But an effect size measures the absolute magnitude regardless of the sample size. So anytime you report the results of a hypothesis test, you should also report an effect size. Cohen's d measures effect size simply and directly in a standardized way. So that's the one I want to show you now. This measure of effect size is called Cohen's d, and it's computed by the mean difference between the treatment and no treatment divided by the standard deviation of the population. So what this is doing is it's saying how big is the difference? How big is the difference between the sample that got a treatment and the population that didn't have a treatment? And we're going to divide this by the population standard deviation, or in other words, how far apart the scores typically are. So if you have a d of 0.2, that means that you have a treatment difference compared to your no treatment people that is about 1/5, 0.2, 1/5 of a standard deviation. If you have a d of 0.5, that means you have a difference between your treated folks and the rest of the population that's about 1/2 of a standard deviation, or about 0.5 standard deviations. And 0.8, again, it's about 0.8 standard deviations different between the folks who got the treatment and the folks who didn't. These here are indicated as small, medium, and large effects. Now, I'm not sure if you noticed, but this formula right here is actually very similar to the z-score formula. Remember that the z-score is the mean minus the mu divided by the standard error of the mean. So that's sigma sub m. But this one right here is not affected by sample size. This is just the standard deviation. Remember that the sigma sub m is computed as sigma over the square root of n. And so it's affected by the sample size, and that's the reason why a statistic could be significant just because it has a huge sample, because the bottom of the z-score statistic is affected by sample size. But this Cohen's d is very, very similar. It's just not affected by sample sizes. And so that makes it able to tell us not only whether it's statistically reliable or statistically significant, but also, does it matter? Is it practically significant? How big is it? How much is the effect? How big is the effect? So, in order to better understand effect size, I have a little illustration here. Let's say that you developed a new treatment for depression. Whenever you're feeling blue, just stop and do 10 jumping jacks and you'll feel better. This is a distribution of the folks who have untreated depression. This is a measure of their mood. This is the average amount of mood. Some people have a higher mood, some people have a lower mood. But this right here is the folks with depression who are doing jumping jacks. You'll notice that this distribution right here overlaps almost perfectly with the folks who have untreated depression. Okay, let's say this time you developed a new medication for depression, and it boosts serotonin in the brain. This time we might expect that mood might actually be improved. So this is folks with untreated depression. This is folks with depression who are taking the medication. Notice that their average mood is much higher than the folks who don't have treatment of depression. This difference between the mean of the untreated folks and the mean of the treated folks is called effect size. It's how much your treatment effect improved the average score. This is a large effect size when they're very far apart. When the two means are very far, large effect size. If they're very close together, this is a small effect size. In that first example where the two distributions perfectly overlapped, that would mean there was no effect size. So, when is a 15-point difference a large effect? It's going to depend on the distribution. If a treatment increases the average score by 15, that could be no big deal, like we see here, or a real big deal, like we see here. The effect size puts the difference between the treated population and the original population in perspective, because it puts it in terms of standard deviation units. By dividing it in by the standard deviation, it puts it in those terms. So in the first example, we have SAT scores before treatment and a distribution of SAT scores after treatment. The mean of SAT is 500, and we think that the mean of this treated group will be higher by 15 points, like we said. So what would your D be here if the standard deviation of SAT scores is 100? Go ahead and take a moment and compute this. You should have seen that the mean of the sample was 515 minus the mean of the population originally untreated was 500. That's a 15-point difference, divided by the standard deviation of 100. That's right here. If you carry that through, your D is 0.15. And in the second case, let's carry that through too. Go ahead and take a moment and carry that through. Hopefully you saw that if you did this, that 115 was your sample size because you increased them by your sample mean because you increased them by 15. So 100 plus 15 is 115 minus the mean of everybody else is 100. So that's a mean difference of 15. And we divide that by the standard deviation in this case, which is 15. And so your D is 1. In that case, you could say this is a very substantial effect size. That's much larger than the standard we gave you before, which was a D of 0.8 is large. Here, a D of 0.15 is very small. That's lower than what we even call the cutoff for a small d, which was 0.2. So a 15-point difference could mean a very small effect size or a very large effect size. Both of these might have yielded statistically significant results. But if we don't also compute the d, we don't know how much it matters that it was statistically significant. All we know is it made some difference, it improved the scores, but we don't know how much until we compute the d. What I'd like you to do now is take a moment and work through this practice exercise. This is the end of the module here. In the general population, the average person scores 100 on an IQ test with a standard deviation of 15. Here's 100 as the mean, 15 is the standard deviation, so 70% of the scores will be between 85 and 115. 95% of the scores will be between 70 and 130. You want to see if having people practice a working memory task can improve their IQ. So you recruit a sample of 16 people, have them do the task every day for a month, and then measure their IQ. Their mean was 110. You need to follow these 4 steps of a hypothesis test to see if the treatment worked, and you can conclude that in a statistically significant way. So follow these 4 steps and see what you come out with. Pause your video, work through it, and then play it again for the answer. Here's the answer. First step, write the null and alternative hypotheses. That should be indicated by the null hypothesis H sub O is that the mean of the treated group is greater than 100. The alternative hypothesis is that the mean of the treated group is less than or equal to 100. Why did I use this greater than or less than sign instead of the equal that we saw earlier in this module? Because there was a word in the problem that indicated to us, going back one slide, that we were asking, can it improve their IQ? Which means we're doing a one-tailed test. Step 2, draft the null distribution, find the critical region. So if we have this as our original population distribution, then we should expect to have a sampling distribution that follows a similar format that has a mean of 100, but a standard error that's computed as sigma, here, 15, over the square root of n. You remember that the n size I proposed on the last slide was 16, so you put your sigma, 15, over the square root of n, 16, and that equals 15 divided by 4, or 3.75. That's the standard error of the mean that goes here. Once we know that, we have to transform this distribution into a bunch of z-scores. So the mean of the distribution becomes 0, and the standard deviation becomes 1, and we want to figure out what is the z-score that binds the upper 5% if we're using an alpha of 0.05. Since this is a one-tailed test, all 5% go in the tail, and the z-score that separates that upper 5% is 1.65. The next step is to calculate the sample's z-score. We do that using our formula, that is, the mean of the sample minus the mean of the population divided by the standard error of the mean. That is 110 minus 100 divided by 3.75, right here, or 10 divided by 3.75, or 2.67. So if our z is 2.67, does that fall here in the body of the distribution or here in the tail of the distribution? You should see that it falls in the tail of the distribution, and we make a decision to reject the null hypothesis. So we would say something like, having people practice a working memory task appears to have improved their IQ, comma z equals 2.67, comma p less than 0.05, comma one-tailed test. Alright, that's it for this module. If you have questions or need any help, please reach out to me, and I'm happy to answer any questions.